literally a lot of stuff. And I've been really working just every single damn 10, 20 minutes I've had in the past days without being able to stream really. And I just kind of wanted to use at least for the next like half an hour, 40 minutes, just kind of do a bit of a recap of what I'm doing because I feel like I'm just kind of writing everything from scratch almost again. Um, and yeah. So, and the title of the stream is Biseparability really punched me in the face the other day. That's the reason why I decided to kind of rewrite literally almost everything, right? And let me try to explain. Let me try to explain what happened. So we'll try to see with maybe with pain. I'll give me a second. I'll be back in a second. There you go. It's always when I start streaming, then the delivery guy comes in, right? Yeah. Okay, cool. So, what I've been doing since now is like I had this idea, right, where, um, you know, you kind of basically have your states. Like, let's say you have your, you know, um, you're starting with this is qubit 0, this is qubit 1. So you start with the 0, 0 state, and then you apply a Hadamard gate, and then you kind of end up with a plus in the plus state, and then you apply a control gate, and so you're kind of doing things like um, with the hypergraph concept, right? You can play with hyper edges in a way that um, to kind of represent the correlations, right? So after a control node here, you kind of have an edge that looks like these. Sorry, that is obviously a 0. And that is obviously a 1, right? So these would represent, and here you have the two qubits and these are the two edges, and the way that you would map that into a state vector, it's like the edges sum between each other and multiply internally, right? So this would be a 0 times 0 plus a 1 times 1, right? So this is the Bell state. Um, and then, the idea is with the way that I was implementing the factorization stuff, the factoring or simplification stuff, I've called it different names across, different stages of the of the library. You could kind of try to merge things, right? And say, look, if my system is in the state, you know, in this state, right? I can obviously merge these because, if I do make these equivalents here, that's like saying that I have the 0, 0 state and the 1, 0 state, which can obviously be simplified in having the plus state and the 0 state. And again, it's maybe not it's not a simplification that you must do, but it's a simplification that you can do to kind of talk about correlations and like it allows you to at least say, look, this system is not entangled because you can actually represent it with a single edge, with a single hyper edge, right? And so the whole, I kind of had based the whole development on around this idea. But then yesterday, I kind of came across. I was like, I don't know why I didn't. I don't know why I hadn't thought about this before. But if you go to, so let me just open Quirk, right? And I'm like, look, you can. I'm like, okay, how would it work if I have this kind of state, right? Like a hardware gate control node. So I do a bell state here, and then I do a bell state here. Your system is still it's 4 qubits, but like you have like your state is entangled, but this state is biseparable. What it means is that you can at least separate it into two parts, even though you can't then really unentangle the qubits, but you can think of these 2 qubits being entangled, these two being entangled, but then there's no real correlation between the pairs, right? And I kind of like I like, okay, so this is the state vector that I have. How would my algorithm work, right? So you go here, you get rid of these, and then you say, look, so now I have my system is in this state, right? So this is really the state that we have. And so I was like, okay, so this is qubit 0, 1, 2, and 3. These are different edges. That's how you would map the state vector to the hyperedge. So this would be hyperedge 0, hyperedge 1, hyperedge 2, hyperedge 3. And this is really Q and Q and Q and Q. And like following the procedure that I had implemented, like you can't, like you literally, the output of my factorization or factoring or simplification method would be like, dude, that's entangled. You can't simplify that, right? Which is obviously wrong because you do want to, be able to find out the fact that you can actually, you can actually do the biseparability thing, because the ideally what you want to have is, what I want to make out of this tool is, you want to be able to explore hypergraphs or systems in hypergraph shape in a way that allows you to explore the entanglement and the correlations and whatnot. And I think it's important if we give, if I give myself the tools to be able to do that, right? Previously, if I would just have run the factor or the simplify method and given it just qubit 2 and 3 as input, it would have told me that it can't simplify because they are part of other edges. I also had made a bigger, sort of a broader mistake as well, which is the whole concept of, unentangled qubits being or having no edge, and then and then kind of, the way that the mapping between state vector and hypergraph was a bit innocent, because I always had in mind that, look, what if we have a system that looks like this, for example? We have these hyper edges between qubit 0 and qubit 1, right? And then we have these hyper edges between qubit 2 and qubit 3, right? And maybe we have another, hyper edge with just a qubit in the state 1, right? In the state plus, right? Like how, like, I was sure this was a valid hypergraph. So this is one edge, this is one edge, there's another edge, there's another edge, right? Like you could, this is a bit of a tabular form, but you could also draw it like, in a non so tabular, like just like a graphical hypergraph, you would do that, right? Now the dashboard, let's see if this, because I want to make sure if anyone has any questions, just to, yeah, cool. So, but still, then I'm like, I always had thought of that the edges were, kind of summing. Like this is the mapping is you sum the edges, or you first multiply the each internal node in an edge, and then you sum the edges. That's how you get the state vector. But then that makes no sense in this setup, because I don't want to sum this edge with this edge. I want to multiply this edge. So this is a flaw. Like this was a big design flaw of the whole thing, right? If I want this to work out, like it's different. I have to, the logic would be, the mapping would be that edges of the same qubits add up, but edges from different qubits multiply. And it's like you would actually multiply, the whole package, right? You would say, this times this, and then this times this. So effectively, you kind of then kind of reconstruct these, right? And then still these times these, right? So if I would do, yeah, or like each separate, right? You can also do each separate, that's fine. And it doesn't matter the order, you're gonna get the same. So these are now the new rules, basically. Um, and I've also kind of had to come up with a different way to like, essentially what I was trying to do with my algorithm for simplifying, where I was just, taking a look at, it was a naive approach. It was actually a really specific case instead of a generic treatment to the problem, right? So if I had this state, what the algorithm was doing was checking edge by edge and comparing, is there only one element that's different? Yes. So give me a second, someone else rang at the door. Cool. It feels like all the delivery guys are just decided to come at the same time. Anyway, where was I? Yeah. So the way the algorithm was working was it was kind of doing like these, right? And then adding this thing and saying, I add these two, so it turns into a plus, and then I have a zero, and that's it. But it's pretty stupid because what I'm doing here is I'm doing two things at the same time. The first thing is what I'm doing implicitly is checking whether I can factor these out of the equation. And what I'm doing secondly is saying if I can, simplify that. So ideally, like in reality, what this is doing is conceptually, right? I keep two edges for qubit zero, edge zero, edge one, and then I have for qubit one separate edge, um, called edge three, that just has a zero value. And then what I'm implicitly doing is I'm saying, well, that's kind of stupid because I have two edges, which is one node, and it's the same like having, because this is the computational basis, right? So I might as well just kind of sum them up and just have like a Q0 and then have like a, another edge, E4, that is just 0 plus 1, right? And yeah, so basically the issue here is that when we have a system like that, you kind of have to have a similar approach, but ideally the way that I've now designed this is like I give the method a list of qubits that I want to try to separate or decompose. I called it, and then what it's trying to do is it's trying to decompose it. So it's saying, cool, so let's go edge by edge and kind of make, by each edge pair and compare. Like for example, let's take this edge here and this edge here. Can I decompose it? I can. The condition for decomposability would be that the nodes are equal, yeah, right? So if I'm doing like a decompose and I give it like Q2 and Q3 as a qubits to decompose, I can take them out, right? So I can take them out, and essentially I'm doing what I just described here. I'm just keeping the edges 0 and 1 for qubits 0 and 1 as they are, and creating a new edge, whatever edge prime that is just 0, 0, right? Uh, yeah, and then I'm like, okay, then I kind of run, these recursively and say, can I decompose these for these two edges? Yeah, the same story, right? So you end up with the H2 sorry, E2 and E3, 0, 0, 1, 1, and then you end up with sorry, it's a mess, with the same, like with the prime prime was like 0, 0, right? So you end up with this setup, and then you can do these things separately if you want. It's not even this thing. It's more like a, how did I call it? Like a simplification, right? You do have edges that are redundant and can therefore merge them. Um, so I call these not composition, but like simplification. That is actually the new the new meaning of simplification, is where you will see the interference happen, right? Because that essentially translates to 0, 0 plus 1, 1 plus 0, 0 plus 1, 1. And so they constructively interfere. Like if this would be a minus, then you'd have a minus here, and these two would destructively interfere. But that's the simplification. I don't really have a better name for these. But so essentially, that's what I've been up to for the past week. Kind of literally rebuilding the whole thing and making it more simple. So I have, and then the idea is that I'm going to make it a bit more flexible for the user to use these as an actual exploration tool. I don't want the tool to automate a lot or to automate too much. It's more like give the user the possibility to operate with the hypergraph in a way that you can explore the algorithms and how the state transforms. And why not? And that's what I wanted to do now, is why not just already generalize that for qubits instead of qubits, right? Because that's what we want to go. We want to make sure that we generalize that, and that we don't just have qubits, but we have qubits of dimension d. To be able to do stuff like toy models of Shor's algorithm and things like these. But basically, the measurement stuff is here. That's still really, it's still qubity, so it's still zeros and ones. This needs to be improved. The rewrite stuff is generic, right? Because remember, the gates are kind of defined like that. So you would have to define gates differently, of course, as the rewrite rules for, but it's going to be the user's responsibility to execute a rewrite operation. And it might happen that the rewrite doesn't work because maybe all the edges are not composed. So a condition for the rewrite to work would be that the qubit map, like you got to have all the qubits composed in the same edges. You got to have them, sharing edges, so that you can actually really run the rule replacement. Maybe there are other ways to run rule replacement without the composition as a precondition, but that would be maybe an exercise for later. But that's like, then the method would spit out an error and say, hey, you got to compose first, or you can't run because the qubits are not composed, stuff like this, right? And so we've got the rewrite block here with all the rewrite functions. Then we've got the decompose block, which is basically this more general idea of, let's decompose these qubits. And yeah, maybe I'll stay at the qubit level first, and we're gonna make sure that this works well, and then I can generalize to qubits. It's probably too early for that, but so we go through these and we take a look at we do a decompose recursive, which basically recursively checks whether two edges can be whether qubits can be decomposed within the context of two specific edges, hyper edges, obviously, and then it does the thing. It's not much different than what it used to be. It's not adding anything else anymore. It's just creating a new edge. At the end, the decompose creates a new edge with the weight 1, right? Because we keep the weight in the other and the other edges, the original edges, and it just moves one node to the new edge and deletes the other one, just for consistency. So this is this, and then we can we can work on the composition now, maybe. I'm not sure I'm going to need the same interface for that we use for decompose, but they're sort of like inverse to each other, right? Compose and decompose. Because with composition, what you want to do is you want to take a look at qubits and see, okay, are they belonging to different hyper edges? Let's compose them, right? So they share the same edge. This means that let's apply the multiplication kind of stuff. Then simplify is the stuff that's going to basically do the comparison between branches and say, look, um, do I have redundant edges that I can get rid of, right? So that's like the redundancy stuff. The splitting states is going to be the method that it's used to say, look, I have a plus state, but I want to split it into a 0 and a 1 and have them in separate edges, just to see this state from a different perspective. That's also, and then merge states would be the inverse of that. And then we have just like a bunch of utilities, the state equality stuff, and the get qubit nodes and all this kind of thing, all this kind of helper methods in here. So it's way shorter, more crisp, and then obviously there's still work to do with the initialization. But that's the gist of it, basically, right? And I'm thinking, what makes the most sense to do given the time that I have? Think about QDITs or think about these methods, because this is a bit more boring stuff, right? I mean, but why not? So simplified qubits, it's rather easy. So because basically first you want to make sure that check if we can decompose. I think it's the same check. Like, I think I could abstract that away as in like are composed. I think I would, because what this does, it trades over qubits, gets the edge IDs and then compares if they are exactly the same as sets. And that is obviously a mistake in here. Exactly. And I think I can just abstract these to a, so if the sets are equals, yeah. So I think I can just abstract that and say self, I'll call this method are composed qubits, right? And so basically if they are composed, then we return the decomposition, else we return I think the signature for this would be that returns list of new edges or something like that. I think that's, yeah, and so this will just return an empty list. Else, at least it should print an error message. Cubes are not composed. So essentially, and this will be a utils method. Call that are composed self qubits. And so the thing that I need to declare this initially here and say, okay, are composed, return if the sets are not equal, is return false. If we go through all the checks and everything's fine, we return true. So this means they're all composed. Exactly. That's good. That's good change. Because I can reuse that, as this is a necessary condition for many things. For example, it's a necessary condition for the rewriting, right? So I'd say basically, if self are composed qubit map, then we do these, else we just print can rewrite qubits are not composed. So that's good. Yeah. Decompose, blah, 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 blah. So yeah, and how would the composition look like? That's going to be, that's a bit more challenging. Compose qubits. So that's the starting point, right? I'm given a bunch of qubits, and first I need to, what I need to do is I need to know, okay, what are sort of the different, what is the set of sets of edges that I need to compose? Because essentially, and I should probably go qubit by qubit. Because what I'm trying to do, right, is I'm back to the pain stuff, right? If I have, let's go back to the example that we had of a system that is a hyperedge. So this is hyperedge 1, hyperedge 2, then there's another hyperedge, sorry, hyperedge 3, and there's like a hyperedge 4, which is like in the plus state, right? And this is qubit 0, qubit 1, qubit 2, qubit 3, and qubit 4. So if I give the method these, right? I'm telling, like, I want to compose these two, so I don't really care about these at the moment. I just want to make sure that I kind of have, like, I'm getting rid of these and I just have the plus state here and here, right? That's what I want to end up having. The problem is, if I go qubit by qubit, I can't easily, because if I, yeah, it's not always the case that you're going to have single qubits. So I can't just go qubit by qubit. I have to find the different sets of edges that need to be combined. Once I find these, then it's just a matter of saying, each edge. Yeah, but that's also not true because I don't want to multiply edge 2 with a hyper edge 2 with hyper edge 3. These don't multiply, right? I have to multiply only sort of the two different groups, and that's problematic. I should be able, what I should try to do here is I should kind of algorithmically build a maybe a dictionary or a list of lists. Yeah, a list of lists, right? So I want to build a list of E2 and E3 and then E4. And so then I know that once I have this list, what I just have to do is I have to say, iterate over this list and say, okay, get these edges, compose it with these, compose it with that, compose it with, like if they're more, compose, and I think that one run is enough, right? Because it's the same as then saying compose this with the other one or whatever. So, but I just need to build up this list first. It's kind of become a bit inefficient now at the point because I don't have a clear association between qubits and edges. It's like I have to literally go through an edge and check the nodes and check the qubit in the nodes to know that. So that's going to be complicated. if I would go, if I kept track of that at the hyperedge level, it would be much easier. The problem is that then every time a hyperedge is created or something is added, then I need to update these. So I need to keep track, which edges belong to which qubits. And here my current, but it's like, well, I do have the qubit edge IDs. So for each qubit, I have the edge IDs, right? So I could use that as an initial prototype idea. So I would just say, for example, so we build a dictionary, and then we say for qubit in qubits, get the edge IDs, get qubit edge IDs, q, and then basically, well, the other way around. So basically do the dictionary D Q equals these. So with these I kind of build a dictionary. And now and at that point I don't care anymore if I am able to just keep unique sets in there. Like if I now manage to, because now essentially what I will have here, is, let's go back to the case 00110011 and plus, right? So, and this is, if I have like Q2, Q3, and Q4, and what I'm doing here is the compose for Q2, Q3, and Q4. So this composition, what will basically lead to is in a dictionary that says Q2 has got H0 and H1. Let's assume this is 0, H1, and H2. Q3 has got H0 and H1, and then Q4 has got H2. And so, okay, what I have to be careful with is, because I can still use this list, but then what I have to just say is, like, if I'm, I can't compose edges with themselves. So I got to make sure that the overlap is different, like that the actual intersection of the sets is 0, right? Right. So what I have to now do is so give the dictionary can compose edges. So now I'm just basically have to say for element in the dictionary in D, right? Base element. So base element is basically an empty list, and then I say enumerate. And so, so what I have is, if I is bigger than 0, or if I is equals 0, what I will just do is just load up the base elements, being basically this in here, else what I want to do is I want to compare if, if self can compose edges, and I give it the the base elements, the base edges, and I give it the or I give it the di and then di minus 1, right? So I take that and then I check if I can compose, then basically compose, the edges, and that's it. So there's no recursiveness to it, I think. So I think we don't need these. Right? Basically what we're doing is I'm building this dictionary and then I'm saying, I'm just doing a pass. Just one single pass is enough. And I'm saying, can I compose these edges? Okay, but I might actually need some recursivity in the sense that, no, because I'm doing, yeah, I will have to, right? Because after the pass, I might have to pop. So after one pass, I will have, like here, I will have, let's say, merge. If I do compose two, then I still want to check what I still want to kind of compose these with the one that was left. Or if I say I will compose these, I want to make sure that I can keep composing it farther. Not with the previous one. That is the uh, that is the. Although that is not a bad algorithm either. Like if I have, element 0, element 1, element 2, element 3. I'm saying like, okay, compose these. So I have 0 plus 1. Yeah, I should pop them out at least and then have 0 plus 1, E2, E3. I don't care. I think I don't care at that point. This doesn't have to be like that. So this can just be edge groups, an empty list. And then what I would just do is edge groups append. And I would append this guy there. Exactly. And so enumerate edge groups. So this will be the base group. This will be the base group, right? This will be the base group. Okay, there is some recursivity going on here. So this will be the base group. Yeah. So it's actually, so that will be the compose qubits. Compose recursive. This is what's going to be. This is compose recursive because what it does is and it has the groups. And it has the groups, so edge groups. And so this is part of the pre-processing that is done in the non-recursive method. So compose qubits, and this just has qubits, and then basically we build that up, the edge groups, and then we're just, return self compose recursive, and we give the edge groups and the qubits. Exactly. So, and then what this does is it takes the base group, it compares like, okay, this base group, and then it's like, can I compose these two base groups? If I so, then I do compose the base groups, and then what I actually do is I pop these two. So this gives me an edge ID. And what I now do is essentially it's the same like these, right? So I'm kind of but from the base group's perspective, right? I just remove these. What I literally do is I literally say base groups pop I base group pop I -1, right? And then base group append, and I append another base group, which is basically the new edge ID, because I want to make sure that now these one can also be composed farther down. And finally, I do the recursive call here, and it says self compose recursive. Yeah, and I just give it the base groups, not base groups, sorry. What am I doing? So I remove it from the edge groups, and then I do edge groups qubits, and at the end of the day, that gives me, so this is the return, of course, and then here, if I go through these and there's no composition, then I just return the edge groups. So yeah, essentially what compose is going to do is going to then return the final composed groups. I think that is a good implementation, and it follows. It literally it's a literally like a mirror of this one, right? It's just that here we don't. Here I'm not adding. I think I don't really have to update the list by adding, because I'm decomposing edges. Return EIDs. What am I doing to EIDs? I'm not so sure if this is what I want to return, really. I want to return the new IDs, probably. So I don't know, something to think about, like whether that's the correct one. But that would be the composition. Now I have to just say can compose edges. You know, can compose edges would be, you know, the so this is base edges can, or base group. That's group, counter group. And so, to be honest, this is return the set of, so the base group set is going to be different. Intersect. Once more, give me a second. Time's up anyway. Oh, Jesus, the fucking delivery guys. Maybe just one little thing. So the base group intersection must be empty. So Python set intersection. Intersection Y. So basically the Python intersection empty Python empty. How do I check that? Ah, okay. If there's an intersection, okay. So basically, bool if there's an intersection, right? So I just say return bool, return like not, and then basically so if the intersection is empty, then we can compose. If not, we can't compose. Awesome. And then the composition is what's left, but I'll be working on this next. Yeah, probably off stream anyway, but that's the idea. You get the gist of it. I think that's a much more sane approach to the whole thing, and it's much more oriented to the actual usage that I wanted to give it. So awesome. Goodbye.